Hey everybody, we're live here. Who is here? I don't know if anyone's here. But we will do some problems. Maybe we'll talk over some concepts for 201. They've got a test coming up on Tuesday, so we might just hop right into it. Let's do that. Let's go over here. Do some 201. We're over here on the main screen talking about some 201. So when we think about it, 201's got a lot of topics on the test. I know, a lot of topics. So let's go right here and let's think about the very beginning of the topics and kind of give some good understanding of what's going on. So the beginning chapters are all about visualizations. So when you think about the visualizations, you need to know there's going to be groups of visualizations. This is like the beginning chapters, like chapters really, we'll start at the very beginning, before chapters 2 through 4, before chapters 2 through 4, which are all basically visualizations. You've got the very, very beginning, which is chapter 1. Chapter 1 is just about variable types. There's a few other concepts like the who, what, when, where, why, and statistics are for samples, and populations have parameters. So there's a few topics, but the main concept is going to be variable types. So we look right here, we have variable types. So when it comes to variable types, you've got things, if you're in the chat, feel free to say hey or ask questions. Variable types are going to be things like categorical, which puts things into categories. Quantitative, which means they're actual real numbers or identifier. So we have these types of variables right here, and knowing the difference between all of them, kind of you can quiz yourself. You can ask yourself, okay, what's a categorical variable? It'd be things like hair color, shirt color, eye color, all those different things. It doesn't have to be color. It could be like favorite video game. Could be what state you were born in, if you're born in the US. All these different things are categorical variables because they put things into categories. Then you ask yourself, do you know what a quantitative variable is? Quantitative variables are going to be questions that are answered with how much, generally speaking, because it's always a quantity of things. It's always a how much or how many. So if you ask, how many miles did you run? How many years old are you? You could say, what is your age? But you're asking, how many years old are you? So you can always phrase these questions in like a how much sort of way that we answer it. Now, identifiers are going to be like a which group, which one. That's probably the best way to say it is which one, because these are groups of one. I did say which groups, but it's a group of one. Identifiers identify, that's what they do. So things like your driver's license, your student ID number, your fingerprints an identifier, all these different things right here are identifiers because they only go to one observation. So if we were to have an Amazon list of orders, we might have an order ID number, and that would be the identifier for that data frame. But maybe we have a different data frame, like a data frame just means an Excel spreadsheet. So maybe we have another Excel spreadsheet where we have people's Amazon customer information, and then we'd have a customer ID number. So identifiers can be different depending on data frames. Sometimes you might have an order number as the identifier. Sometimes you might have a customer ID as the identifier. But the key thing is it never repeats. So I know that's where people get a little bit confused, I think. It's because you'd say, well, wait a minute, how can order ID repeat? Maybe we work at a fulfillment center and we're looking at if there was issues with an order where they sent it back. So then we'd be tracking like issue number or something like that. Like there'd be a report number or a case number. So we could bring up the case number and we could see how many times that order was sent back and maybe how many times that order was in transit or something like that. It all depends on the data set, and we'll make this very clear on the test. On the test, if we ever show you a data set, usually it has ID in the name. Usually, sometimes I should say, very commonly it does, but it could also be things like student number or something like that, which is going to be unique. If we have like a student number and then we have like their profile, or if we have customer number and then we have their profile, it should be something that doesn't repeat, never can repeat. You could basically ask, which customer are you talking about? And it'd go right to that customer. Phone number could be an identifier for companies like Sprint, Verizon, because they would identify that phone line. So, but then they might have maybe a household data set, but we'll make this very clear. I hope I haven't confused anybody, but identifiers, whenever you have a data set, are going to be unique for every observation. And you just have to look at it and you have to say, is this the identifier for the data set? Because it can never, ever, 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 ever repeat. And that's probably the biggest key. One, if you look at a column and you see something repeat, not an identifier, can't be an identifier. Identifiers can be numbers also. You can have someone just have a number as their identifier. But usually you might see letters or things like that. Like if you're looking at like a driver's license number, it might be like TN and then numbers after it. So you can see combinations of numbers or letters or one or other. So that's what identifiers are. I think the other two make a lot more sense. Identifier is kind of the new one for people. I spent more time talking about it. And visualizations right here. When it comes to visualizations, there's a lot. So we really have two groups of visualizations. We have the univariate and we have the bivariate. So with the univariate and the bivariate, we're really talking about two variables and we're talking about one variable. So we've got the two variable versions and the one variable versions. And it's important we kind of know all of them and know how to analyze all of them. So univariate can be categorical or quantitative. And so we're just making subgroups right here. This is within. And a categorical visualization. Wow, so many subgroups. We got visualizations, univariate, categorical. So this would be a pie chart, a bar chart, Pareto chart, frequency table. Hopefully I don't miss any. And a ring chart. I hate ring charts. And I've got a good picture of this. Do I still have that up? I do have a good picture of all these visualizations. I might still have it up. I'll show it here at the end of this. So we have all these different ones right here, and it's important to know how to read them and just know they go together. Probably the easiest thing to remember is that you can make a pie chart of your favorite bars, and you can make a bar chart of your favorite pies. So those go together right here. A lot of people think bar charts might be quantitative because they kind of look like histograms, but histograms is its own thing, which we'll talk about here in a moment. But you can make a bar chart of your favorite pies and a pie chart of your favorite bars. Best way to remember bar charts and pie charts both display the same type of data. A Pareto is a special case bar chart. So we've put them in order. Let's do some drawings right here. A pie chart is going to look like this right here, where we have a slice of pie in it. And a bar chart just has bars. We got a rainbow pen right here. And a Pareto means you've put them in order. A Pareto is a special kind of bar chart that has been put in order. A frequency table just shows the amounts. So you'd have here the counts, the frequencies of each group. So this is a frequency table, just shows the frequency of each group. And a ring chart is basically like a pie chart where the center's been cut out. I don't like ring charts. So ring charts right here are just going to look like the following. Not a big fan of ring charts. So understanding that each of these are showing categorical data and just knowing these, maybe putting them on flashcards, using things like Quizlet, great way to make sure you know these ones right here. And then we get down into the quantitative, and we're just in the univariate. So we have here histograms, box plots. I have to go subbing in on that. Stem and leaves. Dot plots. And I'm doing this all off the top of my head. I'm thinking I'm not missing anything, but hopefully I am remembering everything. This is my kind of quick review and just doing some quick topics. And I'll be putting out some videos this weekend, I believe, doing some speedrun reviews. More fun on that. So histograms are going to look like the following. They look a lot like bar charts, but I guess they kind of are a bar chart of quantitative data. I wouldn't say bar charts are quantitative, but histograms are on a number line. That's kind of the key difference. Is bar charts would have categories here like, sure, whatever the categories are, A, B, C, and that's a Pareto, but still special case bar chart. So bar charts are going to have categories, and it could be like category 1 or 2, but the histogram is going to be on a number line. And that's kind of the big key difference right here, is that the histogram is on a number line and these bar charts are for categories. So they both use bins where they collect the data and you can see how many there are. So you do have like a count over here of how many observations there are in each bin, with maybe like, we'll not put 100 there because we already put 100 down below. We'll put like there's 50 observations in the top bin, and then this goes down by units of however many units it goes down. So that is just a count right there, and we could have the counts over here telling us how many observations are in these bins, such as there'd be 0 here and maybe up to about 20 observations, but that's just telling you the count of the observations in like group B versus group A, and this is how many observations are within this data range of maybe 40 to 60, 40 to 20, 20 to about 10 or so. Bins should be even widths. But if you see, we have more observations near the center of this distribution where the numbers are closer to 50. So the histogram is just giving you a view of the quantitative numbers you have, because your data should look something like this. It should look like 45, 58, 42. You just have a bunch of data here that's actual real numbers. And if you notice, we have a bunch near the center. We could have a 70. And this is what's going to go into this over here. That's what's going to be populating these bins with the data to show us the frequency of the observations. Good morning. Can you go over stem and leaves? You bet. Let's do that. Trace, that's a really good question. Good to see you here, Trace. And you can see right here, this data would look something like it doesn't have to look like this. It would look, does this make sense, Trace? That when we have categorical data, it's going to be categories, and this data is going to populate these bins over here where we'd see, these are each different graphics, but it would look categorical, and then it would populate the graphics right there. So hopefully that makes sense. Hopefully that makes sense. So box plots here, we'll hop down to stem and leaves. Leaves. There we go, stem and leaves. So I don't know how it's spelled. We'll hop here to the new graphic. So can you go over stem and leaves, left skewed versus right skewed? Cool, let's do it. So what we're going to do is we're going to first do a stem and leaf by hand right here. We're going to do a stem and leaf by hand, and then we're going to do a stem and leaf with R using it for us, because it's way easier. A stem and leaf by hand, we first need to do data. So let's say we ask people, how many hours did you study for the test? How many hours did you study for the Stat 1 test? And someone says, let's put it right here. Let's do it with the thing right here. Someone says 0. How many hours did you study for the Stat 1 test, Trace? Feel free to answer if you want. So, hey, Bryce, good to see you here. 474 student, you bet. We can hop over to that in a moment here. You bet. I'm going to get, that's not chatbot. Chatbot. We'll get chatbot loaded up here just so we can track points while we're here. So we'll do that next. We'll do over the stem and leaves right here. You bet, Bryce. We're going to make this right skew. So does this make sense what I'm doing here with the data, Trace? We have the data. And when we look at the data, it's all connected. MuBot is awake. Okay, cool. So maybe you studied 18 hours. Okay, so here's the data on what people studied. With the data on what people studied, we're going to go here and we're going to start making our number line. And to make our number line, we're going to go like this. And then we're going to put here a bin of 0, 0. I'm trying to think how R will do it. We'll see what R does when I do it. 0, 0, 1, 1. Okay, so this is our bin, or our stem and our bins. So these do not represent observations. We need a key down here at the bottom that says something like 0-8 equals 8. So this is the key. Most stem and leaves have a key on it. That 0-8 means 8. So when you think about this, I've taken the numbers from 0 to 9. From 0 to 9, I've cut them in half. So this would go all the way up to what? This bin down here would go all the way up to what? Because I've taken from 0 to 9 and cut it in half. So this would go from 0 to what? What would be the highest number in this bin right here? This would go from 0 to what number? Might not be, I'm going to change this number right here. Sure, that looks good enough now. This 0 right here, because basically, let me make this a little bit clearer. This number range right here goes from 0 to 9. This number range right here goes from 10 to 19. So hopefully that makes, it'd go up to like, it'd actually go up to 4.999999999, because this number right here, technically speaking, it would get super technical. This goes to 19.9 repeating, and this goes to 9.9 repeating. So 10 starts the next bin, and right here, where this would cut right here, would be at 4.9 repeating, and this would go to 14.9 repeating. Does that make a little bit of sense? Like if we have 0, 2, 2, so I'm going to put here a 0, and that's the only 0, 2, 2, 4. I missed a 1, and I missed a, so there's a 1. I should have put these in order. It makes it way easier. 2, 2, 3, 3, 2, 2, 3, 3. Am I almost near myself? 2, 2, 3, 3, and then the 4. It's gonna be right next to me. So there's the 4 right there. And we've now populated this bin. So when you look at this 4 right here represents this observation. This 0 right here represents this observation. This is like the leading number on it, and there is no first number. So we've shown just how to draw the stem and leaf right here, and hopefully make sense of it. The 5 is going to go into this bin, along with the 8 and the 6. I'm going to miss all the numbers. We'll see in a moment if I did it properly. And next, I think we have it. 5, 6, 8. You can tell me if I missed a number, Trace. We can count up here. And then the 8 goes into this bin. Because the 8 right here, this 8 right here is represented by this, but the leading number on it is this. Does that make sense how it's kind of, you know, we could put the key differently down here at the bottom and say 1-8, and that's a 1 now. I should probably make that clear. Those 1s right here. 1-8 is equal to 18. Does that make sense that this is equal to 18? And we're just kind of giving a key for when someone reads it so they can know the units. And we've done it. My hair is just going crazy today. And so hopefully this is making sense how we're drawing this. And now we want to ask, is it left skew or right skew? To ask if it's left skew or right skew, we can draw our little distribution over it. And we can see where the guy's tail goes. So here's our little monster dude. And so it's right to the high, left to the low, whatever way the tail goes. So you might think, so a lot of people would do this. They'd say, okay, wait a minute. Can I select the whole thing? Oh my gosh, I can. A lot of people would say, I can turn this distribution this way. We lost his face. I can copy it, go to a new page, and they'd say, aha, Brian, the guy's tail goes to the low side. But there's a problem here, and this is where the mistake happens with stem and leaves. His tail does not go to the low side, it actually goes to the high side. And you'd say, no, it really does. It goes to the low side, Brian. The reason you're thinking it goes to the low side is because the graphic is reversed. Does that make sense? If you look at the way the number line goes, which the number line's all crazy right now, his tail goes to the high side. Do you see this right here? Like his tail is going to the high numbers. That's why I say left to the low, right to the high, left to the low, whatever way the tail goes. Right to the high, left to the low, whatever way the tail goes. Because his tail is going right to the high side. So if you remember, the tail going to the high side is going to be, and so you can see right here, his tail is going to the high side, right to the high. If you get the number line properly formatted with the numbers going the right direction, it will be to the right side. So it is right to the high when you put it from lowest to highest number. So we can double check our work, which is really great. We could do it in jump, or we can do it, so we'll do it 2 ways right here. We'll go here into R. We'll see a little R for a second. Everyone knows I love R. Loading up R. And let's go here to Untitled. Let's store this in. We've got a comma. Did I not grab all the numbers? That doesn't look like all of them. I missed the 0. Really? That's so crazy. I can just write the 0. Hate when it doesn't copy at all. And so let's go here to numbers. And let's go here to stem. Is it stem? There we go. And here it is. That looks identical to what we were creating right there. This one also creates it downward. So you could just collapse it this way. And if you look at what we've done, and this is why I love using software, because it'll do all the work for you. And we've created the same sort of visualization, a little bit nicer because I can't draw or write. And it does it with the numbers right there. It didn't give us a key, did it? That's really sad if it didn't. And yeah, that is the stem and leaf right there. And if you were to turn it this way, you could see his tail goes to the right because it's oriented the right way. So you can see our little monster dude right here has his tail going to the right. And so there we go. And that is the stem. Is this making more sense, Trace, on the stem and leaf and how to figure out if it's right to the high, left to the low, whatever way the tail goes? We can also do it. Let me do this. Here we go. There's it. We're gonna do it in jump real quick too. Why not? Awesome. It once you see it like a second time, it usually makes more sense. You're like, okay, I've already done this before, and now I'm gonna see it a second time. I sorted the numbers so they're easier to write. 0, 1, 2, 2, 3, 3, 4, 5, 6, 8, 18. So I've got that, and we go to analyze, distribution, we click here, we go here, we hit the stack arrow. You can see it's right skew here. You might say, well, why does this look different? Because of the bin widths. Bin widths are a concept I can mention too right now. Bin widths control how much information goes into each bin, and this looks to be a bin width about 1.25. That's a bin width of 2.5. So to find out the bin widths, you say, I'll show you the mathematics here. To find out a bin width, which we sometimes put questions like this on the test, you go 5 minus 0, and there's 2 bins between this. So the distance of 5 minus 0, we're saying 5 to 0, and we divide that by 2 because there's 2 bins, and each of these is 2.5 apart. Because we could put 2.5 right here. The bin width would not be 5, it'd be 2.5 because the bins are these green bins right here. This is a bin width of 5. That's a bin width of 7.5. That's a bin width of 10. Just notice how the bin width is the width of the green bin, and I'm just changing the bin width, which changes the way the histogram looks. So you don't really want to mess with the bin widths that much, but histograms and stem and leaves can sometimes have different bin widths, as we're about to see right here. Oh no, it gives the same bin width. That's a bin width of 2.5. So if you notice, this stem and leaf looks different, and it does have the key. This stem and leaf looks different than the ones we've gotten that we drew and the one that R drew. This stem and leaf has larger bins than the one R made. R made one just like ours because I kind of guessed what the bins would be. And now this goes right here. Let's bring it over to Word real quick, and then we'll hop to the 474 question. So with this stem and leaf right here, the bin widths are 2.5. So this would start out at 0, and this would go to 2.49. This would go to 4.99. This would go to 7.49. And this would go to 9.9. And these are all repeating 9s afterwards, are all repeating 9s. And this, and then obviously up here. But if you can see, it's going up by 2.5 each time. And so this is where, oh, did I miss a spot? 0, 2.5, 5, and then something's off about this. That goes 0. Oh, and this goes, yeah, it's where it's, let me see, something, that's where that one starts. Something is off. Because this one starts, this has 0 to 2. Oh, it doesn't. Oh, wait, there's 5 bins. That's what it is. Up. Made an error. That's an error. I thought there was 4 bins, and I was like, something's not adding up. This one goes to 1.99. This one goes to 3.99. This one goes to, I can't add today, 5.99. It's the morning. And this one goes to 7.99. I'm really glad we paused because that didn't look right for a moment. So when you look right here, you can see that the 8 goes into this bin because that's the numbers contained in it. So 8 and 9 would go into this bin. And so we just made a little small error right there. But just understanding that these bin widths are bin widths of 2 right here, and probably the easier way to do this, it's much easier than writing all those numbers. I should have just looked and said, these numbers go from 0 to 9, which is a distance of 10 numbers. There's 10 numbers between this. I know it looks like there's 9, but there's actually 10 numbers. The way to think about this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 numbers right here, right? So since there's 10 numbers, I'm just going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there's no 10. And since I've moved the 10 to the bottom as the 0, I now have 10 numbers again. And guess what? I could go right here in the middle of this and do this. And now there's 5 numbers here and there's 5 numbers here. And that's what we're getting if we cut it in half that way, or if we do the bins the way they're doing it. They're doing their bins this way. That was the histogram one. This is the way they're doing their bins. There's a bin, there's a bin, there's a bin, bin, and bin. And this relates to this one right here. So hopefully that makes more sense on the bins and kind of seeing what's going on. There are 10 numbers. I know it's like 0 to 9, but that has a range of 9 if you look at it. But you're counting the 0 as a number. So the 0 is a number, and there's 10 numbers, and you're dividing the 10 numbers into 5 bins, which is 2 numbers in each bin. So hopefully that's making sense right here, talking about the bins and the stem and leaves, kind of a big comprehensive review of what's going on. Please remember that the things right here are not numbers. It's just a number line like you would see on the histogram. So the identical thing you would see on a histogram would be this right here. This is a number line, just like this is a number line. These are not observations. These are not observations. The observations are right here. And we can prove this by clicking on them, and it should highlight them in the stem and leaf. If you notice, this has the numbers between 0 to 2.499. So the 0, 1, and 2 highlighted. So the 2s are inside of this right now, all the observations of 2, and you can see it right there. Can I get it all on the screen? Perfect. So it's highlighting those right there. And if we were to click all the way over here, and I think we could just do that work. That's gonna, we don't need this. We don't need this. Of course, it's not making enough space. Look at that, beautiful. You can see how it highlights the data in both plots. You can see the 8 is highlighted. The 8 is highlighted over here because 8 is between 7.5 to 9.999. And the 8 would be right here, and the 8's over here. We click this, and that's that one observation, which is our outlier. And we do see a box plot here, which is a univariate quantitative. We do see the histogram, which is univariate quantitative, and we do see the stem and leaf. And the last thing we got to mention before we do a little 474, the only other thing we'd have to mention is the dot plot. So we saw the box plot. I do have videos on analyzing box plots. I think I have a really good speed run on that, which I'll send out and make very, very clear. Box plots look something like this, and they're usually above histograms. You can put it below. Stem and leaves show you the numbers. You can put them sideways if you want. So they show you the numbers, and so we put the 5 would go there. And then we could put an 8 there. It's a very small stem and leaf. And dot plots are basically the same as stem and leaves. They just show dots. Not a huge fan of dot plots. It's like, why not make a stem and leaf? So one of the reasons you might not use a stem and leaf, last note on stem and leaves, you might not use a stem and leaf because it takes up a lot of space. If you have a very large data set and you do a stem and leaf, it's going to look pretty ridiculous. We could show that very, very quickly here. Let's go over to the coaster data set. And did it not open? There we go. And let's go to analyze distribution, the height of roller coasters. And you notice how small the histogram and the box plot are. Kind of a nice little distribution showing the right skew. The mean is above the median right here. That's the mean, which we can also see right here in the data. And the median is at 115. So the mean is showing the right skew to the data, right to the high. The tail goes to the high. And now we do the stem and leaf, and it's going to take up way more space, and this isn't even a huge data set. So the stem and leaf, putting this in a report, probably not the best of ideas. You can still see the right skew because it goes to the high side, and you can see they're kind of abbreviating right here with all the data, the way it works. So this represents 10, this represents 20, and they're annotating decimals. There are a bunch with around the 420. They might be rounding it because that's the maximum. There's the observations right here, and you can see we're highlighting them right here. And there is a little bit of variation in there. So all of this is to review, and now let's hop and do some 474. Bryce asks, I'm having trouble with number 3 on the homework assignment. 5, I was wondering if you could go over especially the for loop. You bet. Let's hop here to space. Okay, we're in space. So Bryce, if you're still here, let's talk about some 474. Let's do it. Where is 474? I'm going to bring up the assignment right here real quick. Actually, I think I have it. I think I have it open already. Getting everything open. My hair is just constantly in my face. It's trouble growing your hair out longer. So, and let's see. BAS 474, homework 5 functions. Got it. Got it. Question 3. Question 3. Okay. Here it is right here. Move all this. Okay. Let's do it. Let's hop back in here. Let's see how chat's going. Bryce, yes, I'm here. Awesome, awesome, Bryce. So good. We're going to hop back here to the main screen. Let's do this. Okay, we're here on the main screen, and we've got the question 3. I'm going to try to do parts of it, not all of it. But question 3, let's code the which function written, which function? Write a function called myWhich. It will take an input x vector as a vector of logical conditions and return the positions of the true, okay? If the input is not logical, return the text input is not logical. If the input is logical, finish the for loop in the function and return the position true vector. So there's a key word right here, return. So Bryce, what does return do in a function? Like we're trying to call your attention to this return right here. It's like, if it's not logical, return this right here. If it's not logical, do this, return this. And you might think, oh, I can just like print that. We're not saying print it, we're saying return this. So if it's basically telling you, we're not going to do you could do I don't know, don't do a stop. It says return. And so when you think about what return does, return stops a function. When you hit a return, the function stops in that moment. So the first thing we need to do is we need to think about what we're going to run on this. It says, let's code the which function, write a function called myWhich, which takes an x input, which is a logical vector, and returns the positions of the trues. It will take an input x vector as a vector of logical conditions and returns the positions of the true values. So if the input is not logical, there you go. So when we do this right here, we want to see with this that we actually have it working. Let's try this out. And when we go here, we'll go and look at x, and we'll look at x greater than 0. So we see here we have 3, 4, 5. We have 3, 4, 5. Does this make sense? We have 3, 4, 5. So what should this function return right now? It should return 3, 4, 5. If I run, we're going to put a logical in. This is a logical vector. And if I put a logical into it, we should get 3, 4, 5 return. And does it want us to use a for loop? We can use a for loop on it. Yep. If it would finish the for loop in the function. Sure. Okay. So what we want to do is we want to investigate if this is true. So frankly, we can just do this. We want to go to the first position of this, and we just want to ask, is position 1, and let's just evaluate this. Is position 1 right here, is it true? So tell me right now, what should I do? Should I store this position or should I not store this position? What do you think I should do, Bryce? Should I store this position or should I not store this position? Should I store this position or should I not store this position? Not store it, correct. Yep, exactly. So let's put an if in front of this. If this is true, then we've got the position true right here. If this is true, then run the code and let's store into position true. There's so many ways to do this. Let's store into position true. We'll add to it because, yeah, we'll concatenate. I think that'll do it. Okay, we'll go to position true and we will concatenate position true with position true and put on position true. We'll put onto it 1. And then else, nothing. And that's what you were saying with the not store. So with the not store right here, you've just said if it is greater than 0, position 1, then we will store into the position true vector, which we need to make. This should work. There we go. And so that did nothing, or did null. That's all right. That's what I want. Let's go to 3 because 3 is where we get our first true on this, just so you can see. 3 is where we have our first true. Is it going to work? I think this will work. Okay, it did something, it looks like. It's saying 1. Oh, ha ha ha. Ha ha ha. Let's rewrite this. There we go. Ah, we've done it. I think we've done it. And then this should go to 4. And then there's that. And this should go to 5. And there's that. What do you think I've written right here? What does it look like I've written, Bryce, as I change this. And here's an even bigger hint. What does it look like I've written? Skeleton. Bingo. I'll drop this price. Since you're here, you get this dropped in the chat. There's it dropped in the chat. I'm going to take it out of here in a moment. Other people are going to have to copy that and make sure they get it right with the syntax. It's hard to copy code. It's hard to, like, if you make one error, whole thing blows up. The thing you need to do is test it as you run it. But this code we have right here, we've written the skeleton of the for loop now, and we've tested it out to make sure it works. And it'll go through and it'll check to see if something has a true. Now you might say, this is what I think what confuses people, and it confused me too, is I think a lot of people might be doing this. They might be saying equals equals true. But what you're asking, well, I've got a problem here. We need to do is the position equal to true. But what you're asking, if this is currently equal to 5, then this is currently equal to, it's currently equal to true. So what am I asking right here? I'm asking is true equal to true, which is not a bad thing to ask, but it's redundant because you're just asking is true true. And so, and then you can just use the true or false that comes from evaluating it without having to do is true equal to true. You can just do, is it true? Is this true? Is this false? And you don't need this extra bit. I wouldn't do it this extra bit. Do you have that there, Bryce? And I'm hoping that makes sense of this one, because from here we have the skeleton and a lot of the hard work's done. Awesome. Because now when you think about how to get it to work as a function, getting it to work as a function is going to be, well, one, put this in the for loop. And this is where I kind of want to stop doing the help on this one, because I want to get people kind of to the next level where they have to think about it and be like, what do I do next? And that's the biggest thing, is just working on this in, we know what's coming right here. You work on this in little bits. Little bits is not loud enough there. So you work on this in little bits. You just work through each part of it. And if you get stuck, you ask questions. And you're starting early, Bryce. That's why I'm always glad to put out a ton of help there. It's tough. It's when you get stuck in coding, you're just like, well, I don't know what to do. I mean that's the way I am. When I'm stuck in coding, I'm just like, well, I guess I'm just gonna look at this code for an hour and think to myself, well, nothing. But it helps to get over that hill, and the skeleton should be enough, I hope. From the next step, let's put next steps on here. Next step, create for loop. Creator for loop. Next step, create for loop. Next step, turn into function. And that's it. So we'd put this into our for loop and make sure the for loop runs. And then we'd put this into a function and then make sure the function runs. And we're done. I guess we should talk about the issue with this. We've already got the condition right here. So return. So this should be something immediately. Like, let's just write a function right here. So function, let's just call it, don't do this portion. Hey, Brian, could you help phrase with the function? You bet, Emily, we got this. Test return. Okay, this is going to be a test return right here. And it's going to take input X as we are on our function. This is just a test of it, and then we'll do Emily's question. We're going to do a test return, and we're just going to put here return. So let's do if this right here is not logical, then run the code, return, and then we'll say, what are you doing? It needs to be, or X needs to be logical. Okay, so always try to read your code as a sentence. We have right here, the only thing this function does is it goes in and it checks to see if the class of X, which means that's how R sees the object. So the class of X means how R has the object in its brain. So it's going to say, how does R have this object in its brain? Is it not logical? Is how R has the object X in its brain not logical? And if it is not logical, it'll run this code. You don't need an else here. Technically, we could have just done that. I should just do that because it's not doing anything. It will do nothing if the else is not there. It'll do nothing if the else has nothing inside of it. So sometimes it's like, why put that else there? It's needless code. So just cleaning up our code. So we've got here this, and now let's do the test return. Easiest way to run the test return. Remember that anything you put in here is equal to X. So you could do it this way. We don't get the test return. You could do it this way because there's only one argument. Or you could do it this way. Oh, that's fine. What are you doing? X needs to be logical because in quotes, this is not the logical true. I don't mean in whichever class this is for, but I love. Oh, that's so cool, Nick. Nick, thank you, Nick. That's awesome. It's fun. It's like we've got so many fun things here. We got the prices right too. Hey, Nick, do you want to play the prices right, Nick? Nick, do you want to play the prices right? Anyone else want to play the prices right? I've got the programming prices right here. You have to get as close as you can to 100, and then we're going to do Emily's question. You have to get as close as you can to 100 without going over. Let's turn on the computer audio on this. So we'll see if Nick or anyone else wants to play the prices right for 1,000 points, whichever class you're in, 1,000 points on your weekly total, the winner. Okay, Nick, you ready? I've got the computer audio on. So Nick, and we'll see, Nick, you might have to play against me. Anyone else want to play? Emily wants to play the prices right. I'm going to play too. I'll be first player. So I'll show you how it's played. You ready? So it's going to be Brian, Emily, and Nick. Nick's in the third spot is where you want to be because you get to see. Oh, Bryce. Okay, wait. Exit out of this. Okay, Bryce is going to play too. Okay, we broke it just so everyone can see. I know how to break this function. I entered in a bunch of just like nonsense right here, and that's where the function stops because it says please follow the directions. And look, I'll show you where that is in the function right here. Does everyone see the stop? That created the error in my function because I know it goes into this loop where it says like if your response is not contained in Y or N, because it said, do you want to spin again? If your response is not contained in Y or N after 2 additional attempts, and Nick, you're a mod now, Bryce, Edgio's mod here. So it'll eventually break the function and it'll just stop it and we get this error. So it's important to know what stops are. Stops create this error. Okay, let's go back and play the prices right now. We got 4 players. I'll show you how to play here with Brian, Bryce, Emily, and Nick. Okay, here's how it goes. So Brian, I spin the wheel. Good, I got a 55. Now you want to get as close to 100 without going over. If you go over 100, you instantly lose. So I'm going to take a big chance right here because all the numbers on the Price is Right are 5 through 100 in intervals of 5. So you could get 10, 20, 100, 80, 90, 95, and I might go over. Oh, I got 95. Oh, you're in for some stiff competition right here, and you heard the good sounds. So because I was between this range right here, you see the if the score is between this range to this range, you get the Mario beep noise, just so you can hear that again. And if you go over, oops, oh, wait, oh, cool. Oh, Bryce, you spun at 25. Sorry, I forgot we're in the program. Bryce, do you want to spin again? I spun the wheel for you. I'm so sorry, Bryce. Bryce, do you want to spin again? Yes, I would definitely spin again. 55. Everyone gets 1,000 for playing. Emily, spin the wheel. It's your turn to spin the wheel, Emily. It's going to play the beep noise at the end of this. Emily, spin the wheel. Everyone gets 1,000 for playing. The winner gets 2,000. Emily will spin the wheel here. We'll see what Emily gets. Hopefully someone gets 100. 100 is the big points. I'm going to spin the wheel for Emily in 3. Just type spin in the chat. 2, 1. Here we go. Spinning the wheel right now. 60. And do you want to spin again, Emily? Do you want to spin again with this 60? Do you want to spin again? You're not winning right now, but you are in second place. I should have never played. I've got 95. Somehow I know how to spin the wheel. Do you want to spin again? You're not winning. That's I might play the doom noise. Oh, you don't want to spin again? Nope. There we go. And Nick, it's your turn to spin the wheel. Nick, spin the wheel. Emily's in second place right now. Nick, spin the wheel. We'll see, Nick spins the wheel. 95. Nick, you're tied with me. Nick, we can have a spin-off, or you can go for the win. You'd have a 1 in 20 chance of winning right now. Do you want to stop or spin again? We're going to have a tie. I don't know. Nick might say, I'm going to go for the win. I'm staying. So you see right here, we have Nick and Brian tied, a spin-off. So it luckily, I'm really glad because I thought it would put us both as the winners. So it should say tie. I might be able to, I could recode it. I won't do that now. So we're going to put two more players, Brian and Nick. It's better to go last because I scored. I've got an 80, Nick. Are you ready to spin the wheel again, Nick? Spin the wheel again, Nick. Let's see what Nick gets. You could code the whole prices right into here. Spin the wheel. Oh my god. No, I know, right? Are you going to do it, Nick, or not? It was a 1 in 20 chance. Is it another spin-off? I've seen this on The Price is Right. Go, spin again or stop? Stop or spin? Stop or spin? You might spin. I don't know if you're saying spin again or not. You might be just like... Oh, no! You spun a 90. So you had 170. And so if you get the good play there, Nick, you get the 2000. Oh wait, that's the you got the over noise. This is the you got the 100 noise. I know. I was kind of hoping you would. It's kind of a lot of fun to see. You know, it's a. Oh, I'm playing the beep noise. I was gonna play The Price is Right again. It's just fun to like. You can just put in names and then play and see. You know what people get. Oh, oops! I didn't enter the right thing. Oh no, they got over. Oh, they got a 5? Yeah, so then you can see, oh, one more player. And so there you go right there. It's a fun little thing I created just to, like, I don't know, have fun with it. But yeah, so I like coding little functions. I like practicing. And I thought to myself, I should sit down and code The Price is Right. I think I did this on the plane when I was going to visit my fiance. I was like, oh, I should just, practice coding while I'm on the plane. It's just good practice. You just have to think about what's going to happen and what you'll do next. And so I just went through and coded like it asks you the players. I did want to create a thing called like choose your own adventure. Has anyone done any of those choose your own adventure stories? I wanted to make it so you could write the stories and put in like divergent paths, and you could pick like pathways, and you could say like, I know. I was like, man, watch him win, watch him get 100. That'd be so cool. I really wanted to create like a choose your own adventure creation thing that would you could create your own choose your own adventure, and maybe people could expand upon it online. That'd be so cool. Like, oh, that's a good idea. Like a website where it's choose your own adventure, but people create so many pathways. Yeah, like there's movies like that too. So imagine, no, I think that'd be so cool. So a website you go to and people input routes that you could go down, and people then expand upon those routes. And so you could pick different stories and create like so many divergent routes that you could come back to a story like weeks later and you could try to do the same path, but then it'd be like let's say it's like you walk up and your students could add their own. Yeah, exactly. So you man, this is I kind of like this idea. You pick like it's like you encounter, you're walking over a bridge, you encounter a troll underneath the bridge, and he says, give me $5 and I shall let you pass. And do you give him $5 or not? So you could pick no, or you could pick yes, and then whichever one you pick, there'll be options of which way you'll go. Like if you pick yes, something really good could happen, or if you pick no, something really good could happen, but you don't know. Like each time you do it, something different's going to happen, and it would maybe lead you to different like scenarios and different endings. It's kind of like the Telltale games, and that's where, of course, choose your own adventure classic stuff. But there could be kind of merge points. I don't know, because you'd have to bring people in, because you can't have like, if you have 10 different paths here and 10 different paths here, all of a sudden you get to 10 storylines, 100 storylines, 1,000 storylines, 10,000 storylines. But you know what? I see then I don't know. Maybe there's a way to streamline it and bring it back to like 5 storylines. So people could do that, like loop backs to where you go to a kind of point in a story. Of course, then you kind of notice that you're like, oh, I got this thing that I've heard before. If you get enough people, you could have, imagine if there's 10 parts to the story and literally people write all these things. Yeah. Okay. Let's talk serious here. I like fun ideas. I like thinking of stuff. Write a function called spanage. Write a function called spanage that takes 3 arguments, x, n, and remove na defaults to false. So we've got a default right here. If remove na is true, any NAs should be removed from this, blah, 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 blah. If it's false, they should be left as is. The function should find the difference between the nth largest value of x and the nth smallest value of x. And this is key right here. Okay. So this is a key important part. It should find the difference between the nth largest value of x and the nth smallest values of x, and then divide this difference by the mean of x and return the value. So this is where we really need to start coding something right here, because we need to take a vector x. Yeah, no, this is where to start it. This is where I would start coding. And so it says we need to, and then we have I right here. So if I is equal to 2, it's saying find the difference between the nth largest value of x, and so the I is, let me just double check on the I is. Oh, it's the n. In integer, yeah. I typed I because I was thinking for loops. Okay, so right here, we're looking at the spanage of a vector, and we're going to take the second largest and the second smallest. So how could we get, let's go to nth smallest and nth largest. How can we get the nth smallest and the nth largest? How can we get the nth smallest and the nth largest? How could we get the nth smallest and the nth largest? I'm going to make my vector a little bit harder to work with. Same vector, just doing something to it to make it a little harder to work with. Maybe. You might be right, Bryce. There might be a way. Well, the problem right now is the min is going to get us the min of the vector, which is 1. But I don't think min has additional arguments, does it? As far as I know, min can only get you the min. We don't want the smallest. We want the nth smallest. I don't think we can get the nth using min. If there is a way, I'd like to know. But I don't know of that way. What is another way to get, so what is another way? So the nth smallest right now, if you look at this vector, what would be the second, so the nth just means like the second smallest. What is the second smallest number? Yeah, you're right. No, Nick, we should make this happen. We should make this happen, Nick. Yeah, it's like, that's kind of what Telltale does. If you look at the Telltale games. No, you're fine, you're fine. People should be thinking over right now, what is the end? What is the second smallest of this vector? So you should always think about what you want to return. So we want to return the second smallest. So what number should we be getting? We want to get the second smallest number in this vector for nth smallest, which should be stored into here. Because right now it's 1, and that's not the second smallest. It should be 2. And then the nth largest, which should be the second largest, should be what right now? So the second largest should be what? And then just take a look here. What's this? Yep, Emily, you're on the right track. So we know the answers to these right now for our example, because we're coding like, remember when you code a function, you write one version of it. You don't write the whole function. You get it to work on one instance, and then you make it into a function. So when we think about this right here, how could we possibly find the second smallest or second largest? Maybe kind of we should put them in an order or something. That's not the right code. I think you could do it that way, but it'd be a lot more work. It would require, I'll show you the bad way of doing it. I'll do it the bad way, and then people tell me the good way. So if you go to X, order X, this should, let me look at this. It does. That's too much work. It's too much work to do that. There we go. It's much easier to do that. Does that make sense? Now we've got it sorted. And what do I want right here, Emily? And is this going to get me? Yeah, this will. What should I get right here? What should I get from this? What should I get from this right here? What should I ask of it? How could I always get? And so how could I always get the right number right here? How could I get the right number, the nth smallest? I only want to get one number, and I want to get the number in position what? I want to get the number in position what? What position should I get the number from? There we go. It'll be position 2 because we want the nth smallest. Does that make sense? Now, here's where things get a little confusing. Great job, Emily. 1,000 points. I'm just going crazy this week. I appreciate people being here and interacting. Don't worry. I bet you everyone's stuck on this. I'm going to do parts of it and try to get people further along. I'm probably not going to do the whole thing, but hopefully this is helping right here because we're just coding an instance of this function to get it work on one thing. So when you look at this sort right here, notice how it's not in the right order. What could we do to this sort to make it so the second number would be the second largest at the start of it? Because we could go all the way here to the end of it. There's 1, 2, 3, 4, 5, 6, 7. And we could ask for this, and we would get the right number now. Just so people know, it's not returning 6 because of the 6. It's returning the 6th position in the vector. So what could we do to get... Because here's the thing. And there's ways... Yeah, there's a way to do it that you could do it this way, but I wouldn't. There's a much easier way. How about we take this vector and just reverse it? Well, you could do that too. So there's a bunch of ways to do this. I want to keep this as 2. I want to make sure that's 2 at all times. I could just go to reverse of the vector, and now this will reverse the vector. That's rev right there for reverse, and it just reverses the vector. I wasn't thinking of that at first, though, because I can go here and go to decreasing equals true, and that'll do the same thing, and we get the same thing right there. Now notice what's in position 2 is the second largest, so now we have the nth largest, and did I store? I didn't run this, so it didn't store. We have the nth smallest, and we have the nth largest. Is this making sense, Emily, that we now have isolated those values? And now the only thing we need to do is take this minus this and divide this by the mean of x with na remove, mean of x with na remove equal to true. And that's got it right there. So now we have found the numbers we want, and we'll probably be returning this. So that's a huge portion of this right here. That's a huge portion. We've got the whole thing working, and then we just have to think about what NA remove, because that'll change, because I could put right here choice, and then I could go here and go to choice and put choice as true, and that still works. I could go here and go to choice as false, and that still works. But if I put this now, I think this will still store, yep. Make sure I still get 1.09. I do. So we've basically coded a lot of this. We've coded a lot of this because we have it working with everything we want. We have it working on a single instance. You're getting that right. It might be the 6. I think I had 6 to start. Yep. I had 6 to start and then I changed it. No. Don't worry. Sometimes I just change things while I'm coding because I didn't want people to think that it's actually this, or it was the 6th position in the vector. I didn't want people to think because I put 6 right here, we were getting 6. I always hate it when the same number is used, like in position 6 is the value 6. And because then you might think when I put the 6, it's returning 6 because I put 6, but no, it's because 6 is in position 6. So that's why I changed it to 7. So that way 7 is in position 6 of the vector. So this right here is a huge portion of this question. And if you notice, I went right to where we're actually doing the coding of it, what the function is doing, and then you basically have to start building from here. And it wants it to be called this, actually. That's what it asks it to be called. Then we have to just replace that. So from here, we're just going to build this into a function. And the thing is you never get your function to work as a function. You always get your function to work on one instance. I can't state that enough. When you build a function, you get to work on just one instance. Does that make sense, Emily? It's like when you make a function, one instance. Your function works on one singular instance. Don't get the function to work on everything. Don't be like, I'm going to code the whole function. It's going to work on everything. You get the function to work on one instance. Yep. And from here, we're pretty good. Earlier, you talked about box plots. What would you be? Yeah. And so I do a speed run on box plots. Let me go grab the speed run of it. Do you guys want to see something I'm creating right here? Not right now. I mean, like not creating in this moment. Do you guys want a sneak peek of the videos that are going to come out this weekend, the opening to it? I can get a review of it. I'll see if anyone knows it. Where's the speed runs? The speed runs not on here? Let me see here. Here's the box plot speed runs. These have so little views.
Let's give him a great show, okay?
The one and only.
Oh, you guys can, oh wait, you might be able to hear the audio from that. I think it's, so let's start the, okay, here we go. Was my audio on? Let's check it. Where is my audio? Yep, you guys can hear that. Disney's going to come after us for advertising their video within our video. They'll be like, how dare you give us additional advertising. So there is the box plot review, and we got Among Us being advertised right here, but the clock on this. People want to know the there's Short Hair Brian. Short Hair Brian is on the screen. And in this video, I go through and I walk through box plots. So, gosh, that's the beginning of this year. Beginning of this year, Brian. Man, it's making me feel old. I think that Express shirt had a hole, so I threw it out. Sad when I moved. Look at how long my hair is. Definitely got like a mullet going on. Anyways, I think this was, when was this? Yeah, February 16th, I just gotten like a haircut. It's the last time I cut my hair. As I just reminisce over this. This is 6-7 months of not cutting hair. We just started using the microphone too. All these memories. What else was I was going to show you guys the sneak peek of the thing if you guys wanted. Let's see here. Is anyone here right now? Is anybody here besides me? Let me load up. Let's load this up right here. Let's load up Premiere Pro. You can tell me what you think of this. Let me load up who all is here. Okay. Here is the current project I'm working on. I got this created in After Effects. Let me move this down further. Is anybody here besides Brian? You're here. Awesome, Nick and Emily. I'll let you guys see this real quick right here. So I need to turn on the main audio. So this thing you're about to see, this thing is an object created in After Effects. And so it's like you have to, it's a whole different, it's Adobe and everything. So let me turn on the computer audio and show you what I was working on last night. Oh, good, system audio is still on. So here's what I've got, and I'm going to work on this. Maybe you know this, maybe you don't. And then it's going to, I don't know, I'm trying to do an epic rap battles where I'm going to do like an epic speed runs. And then it's going to like, Brian Stevens versus Chapter 2. And then, yeah, that's my plan. But so got to like glow on doing the different text and the effects. And then like yeah, I don't know. It was fun making it. I was like, I'm going to copy Epic Rap Battles. If you've ever seen their stuff. Oh, thanks, Nick. It's just, I don't know. And then this is all YouTube. YouTube has audio tracks you can use that are safe to use on YouTube. So supposedly I don't have to worry about playing these audio tracks, but I found right where it like the rays in it. And then it's going to be like Brian Stevens. So it's nice because you can see the beats on it. And download a whole bunch of audio tracks, and that one went best with it last night. So I was like, hey, let's go with that. So that's what I'm doing in the background, creating those kinds of videos. I feel like, and I'm going to really try to copy the Epic Rap Battles. We'll see how it goes. If it turns out horrible, I've got the green screen and everything. So once the intro is over, then the video is just going to do its thing. It's going to be me going through a chapter of statistics very quickly. I need to put like a disclaimer on it. That's what I need to do for the first few seconds, is I need to say warning or disclaimer. make sure to study the whole chapter. Yeah, I need to have a disclaimer because I don't want people to think I can cover a whole chapter in 5 minutes. Yeah, I can't. I can't try. Yeah. What are other questions? I can talk about box plots or whatever people want. If you want stat to a one, you call it. I've got a Zoom meeting at 12:30, so don't worry, I've got more time, but I'll probably be heading out very close to when these office hours end. But that's how I have fun. After Effects is such a cool program. After Effects is the funnest program too. You can see I've got, where's my After Effects? That's Photoshop. Don't I have After Effects on my timeline, on my thing down here? You have to go now. You're welcome, Emily. Glad this helped out, and you can come back and review the video. We'll see. We've got a little bit more time right here. I'm trying to think. Might go back to Stats 1 review right here. So that's kind of my default today. Talk about some bivariate displays of data. So we got some bivariate displays. When we talk about bivariate displays of data, we've got quantitative. That's not where we started. We didn't start with quantitative. We started with categorical quantitative. What am I saying? We start with categorical. Okay. So categorical is going to be things like mosaic plots and contingency tables. Thank you, Word. And also stacked bar charts. No one cares about these. See, you can't even spell it. Segmented bar charts. Those, they're not a good display. Really what you want to do is you look at the mosaic plots and the contingency tables. Mosaic plots are the plots that look like this. And I've got whole videos going over these. But these are mosaic plots. Contingency tables show you the numbers inside of it. They've got the counts on the outside too. They've just got numbers. So let's put some numbers. They'd have like 2, 4, and then this could be 3 and 3. So this would be like 1, 1, and this would be 2, 2. So that's a contingency table right there. I had a question that just came up from the quiz last night. Can I ask about it? Yeah, of course. Ask away, Nick. You're more than welcome to. And then stacked bar charts they'll look like a mosaic plot, but they'll be stacked, and they're in my opinion pointless. It's just better to do a mosaic plot. I don't know, maybe just people, because they're not going to show you the marginal distributions. So stacked bar charts are going to look like this, very similar to a mosaic plot, but the widths on the bottom will not actually show you the differences. To say, and here I'll just expand upon that. Nick, feel free to ask the question. Don't worry, this is your time. I'm just filling it with Stat to 1 talk. In a mosaic plot, if we have we have new product and we have old product, and we're seeing if people like it, and so we do like a test market to see people like the new product, and we get a distribution like this, we could see slightly more people like the new product. And let's go here to like and dislike. Oh, oops, wrong side. Now they hate our new product. Like and dislike. So we've got like and dislike right here. But if we did it, and you can see this is the percent of people who tried the new product, and it looks like 20% tried the new product to around 80%. It's just the width of the bars is the marginal distribution. You could also put a bar over here on the side, which is going to show you the overall marginal distributions. This is still for the mosaic plot, and this is for everybody. So this is the marginal distribution of whether people liked or disliked the product. If you turn this into a stacked or segmented bar chart, it would look something like this right here, where we get the bar chart for the new product, and then we get the bar chart for the old product, and you don't have the marginal distributions. So that's why I'm kind of against it. You would get just a distribution that looks like this, and it would look the same, but you don't have the widths of the bars on the bottom. So it's like, why do this? And this is the stacked or segmented bar chart versus the histogram, the mosaic plot. Very, very sorry there. The mosaic plot is just giving more additional information than we would get with a stacked or segmented bar chart. So in my opinion, why do a graphic that doesn't give you as much information? It makes more sense to do with a graphic that also gives you the marginal distributions. That would be a tough test question. Like, what is the advantage of a mosaic plot? It would give you the marginal distribution. That I highly doubt that'd be on the test. It's the key difference between the two. And so it's like, why not if you can just make another graphic? But I was wondering why sometimes when I take the square, yeah, that I need to make it negative and why it needs to be positive? Great question right there. Amazing question, Nick. Great question. Yeah, someone else emailed me about that. So when you take the square root of r squared, here's two plots. You ready? We've got plot A, and we have plot B. So here's plot A, and we have, isn't it? Ah, Charlie, great. Charlie, you got it, because that's what we're going to do right here. Charlie, 1,000 points jumping in. So both of these are going to have an r squared of 0.81. Let's see here. No, 0.64. So both of these have an r squared of, so this has an r squared equal to 64% of the variation in y is explained by the variation in x. And I guess we should do r squared. It's interpreted as a percent, but usually we display it as a decimal. Usually I see it displayed as a decimal. And I'm choosing 64 for a reason. Why, other than Nintendo 64, why did Brian choose 64 right here? Because why? There's a reason. 64 is kind of a magic number for certain reasons, other than Nintendo 64, which is awesome. Man, people probably think about Nintendo 64 the way I think about Atari and Pong consoles. They're probably like, man, it's so old. Because for most people, it would have came out, like college students, it would came out before they're born. Like, yeah, that came out like 5 years before I was born. And 5 years before I was born, I was like, great job, Aaron. Take the square root of it. And when we take the square root of it, you get the plus or minus. So what is the correlation of graphic A? What's the correlation of graphic A? What's the correlation of graphic A? And that's why I chose it. You're right, Nick. That's exactly. What's the correlation of graphic A? What is the correlation of graphic A? Exactly. It's going to be negative 0.8. And the correlation of graphic B is going to be positive 0.8. So they both have the same, I tried to draw the same sort of bands around them. If you look at it, they both have very similar kind of spreads to them. So they're both basically the same sort of graphic. I don't know if I can do this. It's basically the same thing. Took the whole thing. It's basically the same graphic, but I just made one go down and one go up. So they both have the same r squared because they both have the same strength of correlation identical. So when you square root r squared, you have to kind of make sure the slope is either positive or negative because r will be positive or negative. R squared is always from 0 to 1. So a good note that you should have is r squared can only be contained in the value. How do you do contained in? Is it? I forget. We'll do that. Is r squared comes from values going down to 0 and all the way up to 1 inclusive of those values. And then r is within the range of -1 to 1. And so these values right here are the values of r. R can go as low as -1, and r squared is the square of r. So whenever you square root it, does this make sense right here, Nick? Really good question. Just when you square root it, you have to check the slope. You have to check if the line's going up or down. We still got time for more questions. We got a lot of 201 here. Feel free to ask a question, 201. Anything you're wondering about, it is your time to say, confused about this, I was wondering about this. Can you explain this concept? And we can go into detail on any concept. Any concept. I'll let that hang there for a moment. I like editing videos. It's fun. It's like a video game to me, and then you get to the end product, and there's a contest that I think goes till early October where you can like win stuff for like video equipment. I'm like, I should make a big video. I'll probably just lose. Maybe I'll win because I'll be the only person who enters it. I don't know. There's all these like you have to look at the rules of it and like when you sign it. I'm just like, what if they're like, we will own your video content and you will? I don't know. I'm just like, what am I signing? What contest rules am I signing? Let's go back here to our 201 review page. Do we lose it? No. Could you crash course on interpreting regression? Sure, let's do that. Yeah, that's cool. Oh, I wonder what your friend's channel was. We had a guy who we'll do some interpretation of regression right here. So let me get a regression up. One thing we need to know using that website. Oh, we could do, we'll do a crash course on interpreting regression, and then we'll do some normal curve stuff. So when you do a regression, it's only two quantitative variables. And you should say QQ straight enough, no outliers, plot doesn't thicken. Those are the conditions you need to know instantaneously. So let's go ahead and pick two quantitative variables denoted by the blue right here. Let's see if the duration of a roller coaster is explained by the speed. Notice how x is the x variable. It explains, x is the x variable, but x explains why something is happening. Does the speed of a roller coaster, x, explain the duration of the roller coaster, why it's happening? So we do see, ooh, QQ straight enough, no outliers. So we are seeing an outlier right here. We'll continue on, but that is an issue, and this would be a decent test question. This one right here definitely exemplifies a quantitative relationship. It is generally straight enough. You just want to think, does that line go through generally the middle of the data at all points? Like, are there an even amount above and below at all points? Not just even above and below, because the line of best fit does that. Residuals would add up to 0. But does the line kind of evenly kind of bisect the data at all times? Actually, there does look to be a little bit of nonlinearity, and there's a way to check inside of here. I am seeing some nonlinearity. Fit flexible. Fit. Fit flexible. Fit spline. And there we go. Oh, so much output. I just want to look at this real quick. Yeah, I guess the outlier is really pulling it. So that's how I can look at the nonlinearity inside of jump. I can fit a spline, and the spline is a bendy line. It's mostly straight enough. Just at the end, it's got this outlier pulling on it. On my visualization, my y-intercept was negative. Is this okay? Or does it mean I should have chosen a different variable to graph? No, you can get a negative y-intercept, and I might have that on mine even. I don't, which is okay. But the y-intercept, if you see right here, is where x is equal to 0. So it's very important we know when x is equal to 0, we expect y to equal b0. And I'm going to go ahead and take this equation right here. Let's bring this over to a Word document and start interpreting this. So when x is equal to 0, we expect y to equal b0. This equation right here follows the format of y hat. This is predicted y. So that's y hat equals b0 plus b1x. And if you're thinking, what the heck's going on right here, this is really just y equals mx plus b. Now, the easiest way to remember this, and to put it, you definitely should put this on note cards, but when x is equal to 0, we expect y to equal b0. And just think right here, if x is equal to 0, this would go away, and that's what we would have. When x is equal to 0, we expect y to equal b0. And then the other thing to think about is this 1 right here is the slope coefficient. It's this. So the 1 stands for each 1 unit increase. It doesn't literally stand for this. Each 1 unit increase in x, we expect y to increase by b1. For each 1 unit increase in x, we expect y to increase by b1. Or you could say predict, because it's the predicted or expected y value when we solve the regression equation. Another thing to point out here is that all of these y hats are the lines, or the line, excuse me. So these y hats right here are all the values on the line. And then if we had here observed values would be y's. So all of the observed values, which are the dots, are the y's. So kind of just knowing that the observed values are the y's and the values on the line are the y hats. And so when you interpret the regression, I knew it would do that. I always hate, I don't know how to like get outside of this. Let's go here, let's copy it. And then let's go here. Look at that. There we go, look at that, cheated. And so now we need to interpret this. And we'd go, the intercept is when x is equal to 0, we expect y to equal b0. And I always underline these things to make sure you know that you shouldn't just say x and y. You should input the values And then you have to just take the values up here that when the speed of a roller coaster is equal to 0, we expect the duration in minutes to be equal to, and the duration's right here, and I said in minutes because that's the value, the units of the problem. We expect, so I didn't say when the speed of the roller coaster in miles per hour is equal to 0, we expect the duration of the roller coaster in minutes to be equal to 37.74. Now, what's illogical about this? I said when the speed of the roller coaster is equal to 0 miles per hour. So this is a roller coaster that just does not move. I guess it could be like one of those ones where you get on and it's like a virtual roller coaster, like it doesn't move. But by the logical sense of roller coasters move, this is a roller coaster that does not exist. And you can also see that in the data that there are no roller coasters down here at the intercept. This would make this roller coaster a what of the model. Since we're going down here, who knows? This roller coaster down here at 0 that we just talked about with our intercept interpretation, where we're saying when a roller coaster has a speed in miles per hour of 0, because we'd put speed of 0 in right here, and then we'd solve the equation, we would expect the duration in minutes to equal to 37.73 or 74. This is a what of the model, because we're definitely outside of this range right here. We're definitely outside of the range of the x's. So since we've gone outside the range of the x's, we're doing a what of our model right now by talking about a roller coaster that has a speed of 0. Extrapolation, Charlie. Yep. And then we've got the extrapolation down here. And so the model's not really meant to predict right here. That's an extrapolation of the model. So that this intercept does not make sense. This intercept here is illogical for 2 reasons. Well, it's a bad interpretation because it's a very big extrapolation. And then also you just can't have a roller coaster of a speed of 0. It doesn't make sense. The slope is going to be for each 1 unit increase in x, we expect y to increase or decrease by b1. A lot of people put on average. I don't care. My graders better not take off points for that. I don't care. Because expect means pretty much on average. Like, not that it will. Do not put words like will. It's very, very wrong if you say will right here. That means this will happen. The line is just making predictions. And I don't want to write it that way. I want to write it this way. You won't write increase or decrease. A lot of the reasons I put things a certain way is because I've had one student in the past. It's all right. I feel bad now. But I've had like a student in the past who puts like increase or decrease. And they're like, well, that's what you wrote. You said increase or decrease. And I'm like, well, you have to pick. If the line goes up, you'd pick increase. And if the line goes down, you'll pick decrease. What about a roller coaster that is really, really fast? Yeah. So, and it's weird. You would think faster roller coasters would be quicker. But what we actually notice is that there's a relationship. And you see that, look at this roller coaster. This roller coaster is super fast and it's super short. This is probably duration in seconds. I was probably wrong about the duration being minutes. 37 minutes is ridiculous. I didn't look at the units before we started this problem. But this roller coaster is like super quick. It's like probably one of those ones that just like shoots you up in the air and drops you down or something. I guess it only does it one time. But we should be able to hover over this. And the duration is 28 seconds. So it might be one of those ones that just like goes and it might be looking at like the max speed of the roller coaster right here, the top speed it obtains. But this roller coaster hits 100 miles per hour and it lasts 28 seconds. That's going to give you whiplash right there. Oh, it's totally an outlier because usually the faster roller coasters actually last longer, which is crazy. The trend is generally positive. You would think that the slower roller coasters last longer, but the faster roller coasters, I mean, there's ones down here that are fast that don't last as long. But generally speaking, faster roller coasters are longer. Slower roller coasters are shorter for how long you ride them. Would not have expected that. And so for each 1 unit increase, so we'd say, and I should put this, so for each mile per hour increase in the roller coaster, do you see how I'm going to go back up to here? And I'm going to go for each 1 unit increase in x, because that's my x. For each mile per hour increase in the speed of a roller coaster, we would expect the duration of a roller coaster in seconds to increase, because it's positive, by 1.5 seconds. So, and I don't think we can predict at, yep, we can't predict at 150 because that's also an extrapolation. So we can't predict for 150 because, I mean, the line will mathematically predict it. You can just get the line to mathematically predict. And so the line would mathematically predict about, we could go right here, about like 260, 270. And I can't undo this, can I? So you can get it to do it. Jump can do it. There's a really easy way to make Jump do it also. You can go to the data. You can go to this, save predicted. Where's save predicted on here? Should be under line of best fit. Save predicted, there it is. And you go now, and you've got your predicted, and we're using the speed of a roller coaster to do the thing right here. So you could go right here and enter 150, and there you go, 264. So Jump can instantaneously do the predictions for you. And so we could take, so you don't have to actually solve the mathematics. Jump will solve the mathematics for you, but these are extrapolations of the model. And there's the intercept. If you remember our intercept from before, Jump is now just showing the intercept because we entered in a roller coaster that had a speed of 0, and then we just get the intercept right there. You can see the 37.739842, and it even shows you more digits on it. So that's sometimes why if you do it by hand, Jump will do a little more exact calculation because Jump's carrying out like crazy decimal accuracy in the background. But you can get Jump to do the predictions pretty easily by saving your predicteds, which there's just so many tricks. Using, this is what's kind of cool, is if you saw what we were doing earlier, I probably don't have enough time to do normal curve because I've got a meeting in 5 minutes. If you saw what we were doing over here in R, and so I will mention this, we did a good bit of regression right there, and I've got more videos on regression. So please check out the speedrun videos, check out all those. But if you're doing, I think, you're welcome, Nick. I don't have enough time to send that to myself. I've got my own normal curve calculator, but I don't have it on this computer. You know what? 2 seconds. 2 seconds. I got to send it to myself. Shouldn't take that long. Got 66% power here. Okay. Where is it? 2 seconds. You're welcome, Aaron. You're welcome, Aaron. I hope this is a lot of good help right here. Is this it? No, it's not it. I'm not going to find it in time, am I? I want to find this really quick. 2 computer flex. Yeah. Where is it? I called it norm. It was in a, I swear it was in a function file called norm. No. Ah. It shows way, when you search a Mac now, it shows way too much stuff. Oh, I'm not going to find it. I've been meaning to put it on this computer. CDF. What was he at? What do I have? I have like literally, I have 2 minutes. There's no way. It's under documents. I will find this and I'll show it next time because I really want to put it on this computer and I hate to think I lost it because I know. Okay. My Mac's being slow. Well, Jason, we need more time. Jason, we need more time. Bye, everybody. Jason's saying we gotta go. Jason, we just need to film for another 4 or 5 hours. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.